You have to know the graph of natural log of x in this class to survive. Thou shalt know thy graphs. I think I even said that as one of Mr. Wade's 10 rules, one of Mr. Wade's 10 rules back in integrated 3. You must know your graphs. Oh no, Mr. Wade, we're the COVID kids. We forgot everything. I forgot how to graph natural log. Okay, here we go. If you ever forget how to graph natural log, there are certain things you're supposed to know already for this class. The natural log of 1 is 0. That is a mathematical fact. Talked about many times in integrated class. The natural log of e, this is also from pre-calculus. Natural log of e shall always be 1. That was in integrated 3 also. So those are the two natural logs you want to know with no calculator, okay? Natural log of 1 is 0. Natural log of e is 1. And by the way, there's a third one if you want to go through this. The natural log of 0, you can only take the natural log of a positive number. You can't take the natural log of 0. And you can't take the natural log of a negative either. Okay? So if you ever see a circumstance where you have natural log 0, natural log negative, those are capital D-N-E, which stands for does not exist. You can't do those, all right? Impossible. Okay, let's go back to here. Let's think about middle school. Input, output, input, output. What is an input, output? Input, output is just an XY coordinate, isn't it? That's the point 1 comma 0. That's the point E comma 1, remember? So these are coordinates that must lie on this graph. So graph the point 1, 0. Right 1, up or down 0. If you want, this is optional, graph the point E1. Right E, wait a minute, let's put a 1 here. Right E, who remembers what E is? Wait a minute, that was an integrated 3. Just put E, but remember E is about 2.7. So I made it like a little bit more than double the length there, just for scale. So go right E, up 1. Right E, up 1. Let's call that 1, okay? So this graph must hit both of those points. Now, one more important point to make here. The natural log of 0 is impossible. Why? That's an input, that's an x coordinate. Why can I not get to x equals 0? I can get to x equals 1, x equals e, but not x equals 0. Because there is a vertical asymptote right down the y-axis. You remember when we graphed the logs back in integrated 3? Vertical asymptote. You can't get to the y-axis. It's impossible for a log graph at least. Not for other graphs, but for a log graph, it's impossible, okay? And then, let's put an arrow. Remember the curve? Slowly pulls away from the vertical asymptote, hits the 1, hits the E, levels off and becomes the weakest rising graph we'll ever study. It's gradually rising. And you can go out of the solar system, it will eventually hit the ceiling. That's how slowly it's rising, okay? And of course, if you trace it closer to the vertical asymptote, it gets closer and closer and closer, but can never quite touch, right? You can never quite take the natural log of 0, but you can take the natural log of like 0.001, like a sliver to the right, but just not there. So you'll never quite get there. That gap narrows, okay? All right, now the easy part. Take the derivative. Okay, we have two options. We could write g prime of x. I also want to show you another fancy notation that you might see in college, a lot actually, and a little bit in high school. Instead of writing g prime of x, we could start with that. So it's okay to write g prime of x. I want to show you the other alternate notation. And this is going to look pretty wacky here. It's d over dx with the g of x on the side, okay? That stands for derivative, d is derivative, of g of x with respect to x, okay? It's just a fancy form. You probably want to get familiar with it. I'm going to use it occasionally. They'll use it a lot in college, okay? means the same thing. So that's our fancy notation right there, all right? By the way, earlier when we said y prime, remember that one? Y prime can also be written as dy over dx. That's also acceptable. So there are 4 different notations. The primes are the most common, okay? dy over dx, and then I just replaced y with g of x over here. Since natural log has a steepness, it must have a derivative that tells you it's super steep and then super shallow. Well, it does. The derivative of any natural log is 1 over the base. The base was x. The base is the thing you were taking the natural log of, okay? So it's 1 over the base. That's it. Easy, right? Really easy one. And that describes for you the steepness of this graph, okay? And you might be thinking, what does that mean? Let me give you an example. All right, so you see next on the paper here, I ask you to find g prime of 10 because I want to give you a concrete example. Mr. Wade, how do these derivatives actually help us understand? Like, how is this derivative actually working? Okay, g prime of 10. First, what does that mean? From all the way back in middle school, when they ask you to find f of 10 or g of 2, or now it's g prime of 10 means go find the g prime equation, take 10, and stuff it in for x, right? That's what it means. So g prime of 10 equals 1 over, insert the 10, 1 over 10. That's it. Go find the derivative and stuff in 10. So the derivative is 1/10. Now what the heck does that mean in real life? Didn't we say that derivative is slope? Integrated flashback. Slope is rise over run, isn't it? Remember those old days? Heck, that's middle school flashback right there. When I say that 10 gets plugged into here and the outcome is 1/10, that's an input, that's an x coordinate. The outcome is not the y coordinate as it was for every class you've ever taken. Input is an x, output is a y. That's been your whole life that you've been learning mathematics until today. If it's the derivative, the output's not a y coordinate, the output is a slope. Here, I'll just bend the arrow down to here. This is a slope. That's an x coordinate. So the derivative is not the original function. It's no longer giving you y coordinates. We're now talking about slopes. What the heck does this mean? Okay, let's go to x coordinate 10. On my graph, 1, that's like 2.7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where's 10? Roughly about here, right? Okay, just approximate it, doesn't matter. So x coordinate 10, when you go to x coordinate 10, the slope is rise 1, run 10. You know how shallow that is? So the mathematics today called a derivative has proven beyond a shadow of a doubt that on the natural log of x graph, if you go to x equals 10, which would be that dot right there on the graph, the slope is rise 1, run 10. That's very shallow. The stair step, imagine stairs where it goes up 1 foot, run 10 feet. Up 1 foot, run 10 feet. You know how shallow that staircase is? My gosh, you'll never get upstairs. The staircase will have to be like a whole block long before you get to the top of the stairs, right? Very shallow, okay? 1/10, rise 1, run 10, very shallow slope. And you can see it on the graph that it's shallow, all right? So these derivatives are actually measuring how steep the actual picture is, okay? This is gonna be a huge breakthrough later on. All right, example E, y equals 3 to the x. This is not a log function, this is called an exponential function. Boy, let me tell you, you all made A's in integrated 3, so I know you remember exponential growth, exponential decay, that's for sure. Okay, if the x is up here in the exponent, and then the number is in the base, now it's called an exponential growth in this case. Oh no, Mr. Wade, I forgot how to graph exponential growth. Well, give yourself a little reminder then. If you plug in 0 for x. Remember, that's like the easiest number you can ever plug in. If you put in input 0, what's the outcome? What's 3 to the 0? 1. Always, right? So input 0, output 1. Remind yourself that 3 to the x goes through the point 0, 1. So 0, don't go anywhere, up 1. Your graph must pass through that point. And you must be able to graph exponentials in this class in like a millisecond, all right? Now remember growth? Growth goes skyrocket. But then what about the other way? It comes down lower and lower, but it never quite gets to the x-axis, because what's on the x-axis? Horizontal asymptote. Remember that? This is like the cockroaches and investing money in Coca-Cola and all the stuff we used to do in integrated 3, right? That escalates through the roof. All right, does exponential growth have a steepness? You betcha it does, and it gets super steep. Let's go where we never went before in integrated 3. How steep is it using a derivative? A derivative is a master formula for all the steepnesses at all the infinite points, okay? So we write y prime, or we can write the fancy notation, dy over dx. They really like the dy over dx in college, but y prime is fine. It's more practical for now. Okay, what is the derivative of an exponential growth or decay? It's the same formula, growth or decay formula. Okay, this one has 3 steps, all right? I'm gonna teach you every basic derivative rule on day 1, all right? Then we'll get to the more complicated derivatives. So 3 to the x, the first of the 3 steps, write down exactly the entire problem. Just write down 3 to the x again. It just replicates itself, okay? What's the only formula strong enough to examine or measure exponential growth? Another exponential growth formula. That's the only one that can handle how insanely steep these slopes are gonna get. Okay, that's step 1. All right, so we write it down, times step 2, natural log of the base. So you actually get natural logs and exponentials when you do derivatives, okay? Natural log of 3. And then there is a third step, but we don't even have to do that today. That won't happen until probably the next lesson, okay? The third step was times 1, actually, but that won't make any sense to you until I do the next lesson. So for now, that's your derivative right there, okay? So copies itself times natural log of whatever the base number was, which is there. All right, 2 more quick ones here, quick and easy. Arctangent, you probably, well, you had to have studied arctangent in pre-calculus. And often you saw it written as inverse tangent. It looks like tangent to the negative first power, but that's actually not a power. So inverse tangent, arctangent, they're almost the same thing. There's a slight difference. We'll get into that later. Hopefully if you had a good pre-cal teacher, they got into that. But here's the scoop, kids. The first time I've used that one this year. All right, how do you take the derivative of arc or inverse tangent? First, you write y prime, or fancy version, dy over dx. Okay, when taking the derivative of arctangent, sometimes labeled inverse tangent, even though they're not exactly the same thing, you draw a fraction bar. This is kind of like the natural log problem, actually. You put 1 over something. 1 plus whatever's sitting here, called the base squared. That's it. All right, one more thing to memorize, and that is letter G. Arc sine. You probably did arc sine somewhere, I hope, in pre-calculus, also known as inverse sine. Even though they're not the same thing, they're closely related to each other. They're almost the same thing, okay? How do you take the derivative of arc or inverse sine? All right, simple rule. Y prime equals fraction bar, just like last time. 1 over, just like last time. Now, this one has a twist. It's got a square root and then the 1, but this one has minus the original base squared. The base was x, you square the base. That's it. Okay? So this one has the radical and it has the subtraction instead of addition. That's the only difference. They're very, very similar. Okay? All right, so just memorize all these rules and you'll do them so many times over and over again through lots of applications. Don't worry. These formulas look so unfamiliar right now, they will become like 2 + 2 = 4 to all of you, okay? Because you're all very bright. So we'll do these 1,000 times. Now, if any of you clever kids out there are thinking, Mr. Wade, where's arc cosine? You got arc tangent, you got arc sine. Is there an arc cosine? There is. But arc cosine does not come up at all in high school calculus, and it rarely comes up in college. It does not come up in the first few years of college calculus. So arc cosine, they don't want you to know that one, okay? If you're curious, you know, I'm curious as a cat. Probably one of my friends call me Whiskers, right? So the arc cosine derivative is just a negative on the sine formula. That's all it is. But, you know, again, it doesn't come up. Now, one more thing, if you want a nice little mnemonic device, how do you keep all this stuff straight? How do I remember that arc sine is the one with the big square root on it? Okay, here's a little mnemonic device for you. Arc sine has an S. The sine has the square root and the subtraction, right? Arc tangent has a T, which looks like a plus. And that's how you can lock it into your brain. It's very nice, okay? Just so happens that square root and subtract in English all begin with an S. This wouldn't work so well if we were teaching in Argentina or Germany or somewhere else, but it works great here. So that's your trick, okay? Now let's do one last one called letter H. This is about something called piecewise functions, which I think we even did a little bit of. We did it in integrated 3. Hopefully you did a little bit in pre-calculus. All right. You'll know it's a piecewise function when you see the curly bracket, okay? Get ready for some major integrated 3 flashbacks here. X squared is a what shape? Parabola, right? Natural log of x. And then shifted, remember all this stuff in integrated 3, shifted up 3, that's shifted up 2, remember that? Natural log, didn't we just graph that a second ago? Looks like this, right? Asymptote. Okay, a piecewise function, this shape is gonna be half parabola, half natural log, glued together. Or they actually might miss each other. They can also miss, okay? The parabola will only be less than 1 to the left of 1. The natural log curve will only be greater than or equal to 1 or to the right of 1. So now you know who's on what side. So we're gonna cut these graphs in half and glue them together basically, okay? Take where they meet. They meet at x = 1. That's where they're gonna be connected, or they might miss each other also. The 1 is where they're trying to share, okay? Like an interstate off-ramp turns into the city streets, or the on-ramp turns into the interstate. That's the connection where they cross from off-ramp into street, on-ramp into interstate, okay? The changeover. This is called the phase change. It has a name. So I want you to circle the 2 1s and write down phase change. All right, so I just erased it. So what do you do with the phase change? This is what I recommend to all my students for decades now. Take the phase change, plug it in to the curve. 1 squared is 1, plus 2 is 3. When I plug in 1, the output is 3. So I must make sure the parabola hits the point 1, 3. Okay? Now let's try it here. 1, phase change, plug in the phase change. It's very wise to take the phase change and plug it in immediately. Natural log of 1, oh, we did that earlier. Natural log of 1 is 0, plus 3 is 3. Input 1, output 3. Hey, look, they don't always match, but this time they do match. That means the interstate is connected to the on-ramp, because if these are 2 different numbers, which can happen sometimes, that means they're disjoint, they're broken. That means somehow like the bridge collapsed and it's not connecting to the road anymore, okay? So that's an interesting sign right there. All right, now we need to graph that. Now, before we graph it though, things in calculus tend to come in threes. I don't know why, it just happens, but things come in threes. And this is our first opportunity of the year to play our new favorite game called Three Things. Okay, three things. Three things will happen when you graph a piecewise function. What's a piecewise function? Two or more graphs, pictures, fused all together. Okay, so three things will happen. All right, number one, they will fit together. Think about like two pieces of pipe under your house that like takes the water through your house, right? The two pieces of pipe should fit together smoothly, okay? So that's what I call the smooth fit. Okay, we're just speaking colloquially here. There's no professional math term smooth fit. Now, number two, what if there's a crooked fit? You do not want pipes under your house to have a crooked fit, like a right angle. The water's never going to get around that. Well, maybe the water will, but the sewage won't. Yeah, yuck. So, smooth fit, crooked fit. There might be a crooked fit here. And number three, remember I said they could be broken, right? That's called a jump. Okay, like the interstate doesn't even connect to the bridge anymore, the on-ramp, because there was an earthquake or something, and they're totally separated. Okay, or the pipes under your house are completely separate. That's bad. All right, so it's called a jump, or it's also called a disjoint. Okay, so those are the three things that can happen. Let's go to the graph and let's see which one of these three things happens. Okay, well, we already do have a connection. The pipes are connected because they have the same endpoint. So I guess this one's going to be out. So it's either going to be a smooth or crooked fit. Okay, where do you start? Just start on the top. Just do the first line and then do the second line. Okay, shh, quiet. Now, 1, 3, the coordinate 1, 3. Right 1, up 3. Do I put an open circle or a closed circle? You remember this from integrated 3? Not underlined, open circle. Okay, there's an open circle at 1, 3. Now simply graph using your knowledge from integrated classes. What is this? Parabola shifted up 2. Picture a parabola sitting on the origin, but we're going to shift it up 1, 2. So isn't it going through here now, right? Can you picture it? Goes right through there. So you have to remember your integrated 3 basics, of course. Oh, by the way, less than 1, left of 1. It's over here. It's not over here. It's over on the left-hand side. Parabola, shifted up 2, and then dead ends right in that open circle right there, okay? It's the left half of the parabola only. Okay, now we go to the second line. Graph the point 1, 3, which we already graphed. But it's underlined, so it's a closed circle. Remember those days, right? And so the closed circle actually ends up filling in the open circle. So that is possible for a closed and an open to be stacked on top of each other, and you only see the closed circle. So underline, closed circle, then go over here and say, what am I drawing? This shape, okay? You won't even draw the vertical asymptote because it's over here somewhere. So draw what you know to be a natural log curve that comes out of this point. Okay, so here's the whole thing, but it's only greater than or to the right of 1. So picture the whole thing, okay, get your arm ready to go and only draw that much of it, okay? And I actually don't know, just glancing at this, if those two pieces of pipe are a smooth fit or microscopically they could be a little crooked. All right, so let's get to the bottom of this mystery. Is it a smooth fit or is it a crooked fit? It's microscopic if it is crooked, and the human eye cannot tell if that's crooked or not. You can't just look at it and tell. You have to trust the mathematics. What defines steepness? The derivative. How do you take the derivative of f of x? You call it f prime of x. F prime of x. How do you take the derivative of a piecewise function? You take the derivative of each piece. It's just 2 derivatives, okay? Rolled into 1. Draw your curly bracket. It's all on the wrist. Draw yourself a nice little curly bracket there. Let's take the derivative of x squared plus 2. What did we learn today? Let's see if you know. All right, derivative, bring the power down to the front, 2. Step 2, base x stays the same. Step 3, subtract 1 from the power, and the 2 drops to a 1, or just put 2x. Do you remember the derivative of a number, a constant? The derivative of a constant, since it's x to the 0, 0 comes down, gone, 0. Okay, disappears. Okay, let's see if you remember the natural log trick today. How do you take the derivative of natural log of x? 1 over the base x, just 1 over x. What about that plus 3 right there? Plus 3 constants become 0, gone. Okay, that's your derivative. Very simple. One more thing though. Add the parameters here, comma x less than 1. This derivative or slope will only work for the parabola, and the parabola is only less than 1 this way. This formula will work for the natural log graph, but that's only on the right of 1. It says so right here. So don't forget to put comma x greater than or equal to 1. Okay, so you just transfer that down to here, and that is the derivative of a piecewise function. Okay? All right, so it says find f prime, let's put it over here, at -3. Now, I need to plug -3 into the derivative. Here's the question. Do you plug it into the top one, the bottom one, or both? That's another 3 things. 3 things, top, bottom, or both. Okay, where is -3? -3 is clearly not larger than 1. -3 is less than 1, so you plug it into the 2x formula, not the 1 over x formula. So 2 times -3. Just put -3 right into that formula, and you get -6. There's your answer. But what does it mean? What does that actually mean? Input x coordinate at x coordinate -3, not the y, but the slope is -6. Okay, x coordinate -3. That would be like -1, -2, -3, somewhere over here. At x coordinate -3, if you go up here until you hit the graph, it'd be like right about there. What's happening at the graph when the x coordinate is -3? It is, the roller coaster is falling, it's dropping. That's why the derivative is negative. The derivative, the math knows what it's doing. It understands the situation without even seeing this. The math knows, oh, you're dropping on the roller coaster. You're falling, okay? That's what that means. All right, one last problem. I want you to find f prime of 1. Very strategic that I picked 1. I wonder why. Why would Mr. Wade pick 1 of all numbers? Oh, because 1 was very special in this problem. 1 was the phase change, right? It's the phase change. Okay. Now remember what we just said over here? With this -3, what did I ask you? I said, do we plug it in the top? Do we plug it in the bottom? Do we plug it in both? Okay. The number 1 is greater than or equal to 1 because it's equal to 1. 1 is not less than 1, but isn't 1 like right at the barrier between the 2 graphs? So if you're at the phase change, the only proper way to find f prime of 1 is you have to plug it into both top and bottom equations because it is the phase change, okay? I'm going to split this here. So with the split, we're going to plug in 1 to here and 1 to here. This is only for the phase change that this happens. So what is the slope at 1? Does this graph look like a pretty smooth fit just by the human eye? It does look like the 2 pieces of pipe, or maybe these are 2 roadways, right? It does look like the roads fit together smoothly, right? But remember what we said about how it could be microscopically off? Okay, trust the math, not the human eye. Take 1, plug it in the top equation. 2 times 1 is 2. What was the top equation? That was from the parabola. The parabola is steepness 2, basically. Isn't that rise 2, run 1? Take 1 and plug it in the bottom one. 1 over 1 is 1. What was the bottom formula? That was for the natural log graph, which was this part of the road or pipe. The slope at the phase change of the natural log curve is one which is different from the parabola. It's a different kind of steepness. So these are actually crooked, and you can't just trust your general graph. By the math, they're actually crooked. So what is the slope at the intersection? It was a crooked fit. If it had been a smooth fit, these would be the same. What is the actual answer for the slope or derivative at 1? If these match, if this was like 2 and 2, the answer is 2. If they mismatch, the answer is does not exist, because they must match to get an answer. So crooked fit, the answer at the phase change is does not exist. There is no defined slope right there because they don't even intersect each other at the same slope. Okay, that's just a crash course on just the basics of calculus. And then we'll just keep building from that, all right? No homework because you're in BC. You went through a lot of information on the first day. I've given you no homework. I'm gonna let you apply this when we do lesson 1-2 together, okay? So you can still ask questions in class next time about how all this stuff works if something didn't make sense. But no homework for now, just note taking, all right? See you next time.